Hello everyone, I am Kiran Pillai and I will be representing my team Quantum Ledgers for the problem statement SIH 25169 given by ISR. Lunar Orbit, autonomous navigation of robots for lunar habitats.
On the moon, there's no GPS, visibility is inconsistent, and dust is everywhere. And both indoor habitat corridors and outdoor regolith fields are tight on margins for the error. Our goal is to recover the autonomy to patrol, map, and monitor habitats so astronauts can focus on science and critical operations. The end product is a modular ROS2 stack that uses 3D LiDAR, stereo cameras, and IMU to localize and plan the paths robustly.
Traditional 2D simultaneous localization and mapping SLAM stacks assume flat floors and dense features. They can fail in lunar scenes with slopes and sparse geometry. We elevate and include 3D LiDAR to a primary input while still serving real-time navigation. Concretely, our pipeline keeps the full 3D point cloud for high fidelity mapping and drift bounding, and in parallel generates a tunable 2D slice for fast map and blacken. Camera aided texture and semantics where LiDAR intensity falls off. And in the IMU, it stabilizes post through slip, vibration, and brief sensor loss. To mitigate dust, we combine intensity thresholds and temporal filtering on LiDAR returns.
Our production pathway is simulation first, deployment ready. The same ROS2 and F2 launch files and nodes run in Isaac Sim during tuning and then on the rover, reducing custom glue code and expensive field retries. This cuts cost and lowers risk. We profile timing, test new events, and verify indoor to outdoor transfers before touching hardware. The stack is modular. Perception, mapping, planning, and monitoring can be upgraded independently, and we can swap backends. Example, alternative SLAM or terrain relative alignment without re-architecting.
Welcome to LunaBot Phase 1 prototyping. In this prototype, as you can see, we have loaded the surface of the moon through an SLDEM file available via USGS. The actual robot present is the initial prototype with an LiDAR or LiDAR. We have used a 3D LiDAR in order to simulate the environment and check for displacements around. As you can see, the entire robot is mapping out the region. The 200 by 200 region is mapped out via a LiDAR. We have initialized LiDAR point 3D clouds to convert it into laser points so that it can be visualized via RViz. This allows us to see if the actual localization and mapping is taking place. The map is being generated, and this allows the odometry of the robot to be sustained. Hence, our prototype is working. It is detecting, it is mapping, it is using the SLAM toolbox with LIO, SAM, and FastLeo as experimental setups. As you can see, the entire robot travels on its own, and in the windows itself, there are a publishing rate subscribed to the CPU. The publishing rate allows only 0.100 Hz. That means the subscribing ratio is a little bit less due to CPU constraints. Continuing on at a powerful machine will definitely help us. Thank you.